Okay, well, thanks, Cody, for the introduction, and thanks to the organizers for inviting me. It's been a very interesting workshop so far, so I hope not to detract from that. So what I want to talk about today is joint work with Alessio Spantini, and sort of along the line of filtering, and so you've seen a lot of sort of various approaches to filtering before, and this is going to be kind of in the theme of can we devise relatively practical methods that can use small ensemble sizes along the lines of an ensemble common filter, but that can nonetheless start to capture some of the start to account for nonlinearity in a principled way. So that's kind of what we're trying to do. So just kind of set the stage. So this is a picture from NCAR, and as you all know, I mean, especially in kind of the geophysical setting, state estimation, or better yet, joint state and parameter estimation in Bayesian setting is a very desirable goal. And what we'd like to do is come up with algorithms that can recursively characterize the posterior of, for instance, the state of the atmosphere. Here's a picture of a weather forecasting exercise, sequentially as new data arrive in time. And the setting here is really one where the state is going to be very, very high dimensional. And I'm not going to do an example problem nearly this glorious towards the end, so I'll just sort of take that off the table. But this is what we'd like to sort of get towards. And we like to do this in a Bayesian setting. In that sense, we want to characterize the posterior, but we want to do that recursively, sequentially, as data arrive, with sort of constant work per new observation. So if I abstract this problem, I can think of this, I mean, as we've seen in many other talks, as a nonlinear non-Gaussian state space model, and maybe just to set notation. Here, these blue nodes Z represent the state, and there's some transition density, so I know the density of zk, condition on zk minus 1, so I'm already in a discrete time setting. I've discretized my SDE or SPD, or wherever it's going to be, into some finite set of time steps. And there's an observation density that says this is a probability density of observing my observations Y given that the state is Z. So from this setting, one might look at this graph and think about problems you'd like to solve. And a natural problem, sort of the overall problem, is that I'd like to recursively update the full Bayesian solution. So the joint distribution of all the states, Z0 through Zn, condition on the data obtained till time n, and then I get a new piece of data, and I'd like to characterize that new distribution, which is, of course, growing in dimension. And I want to essentially propagate the information of new observations all the way back to earlier states, insofar as they have influence. So that's the smoothing problem, and I'm mostly not going to talk about the smoothing problem today. If I have some time towards the end, then I'll talk a bit about smoothing. What I want to focus on today is an easier problem, which is basically trying to approximate a marginal of this joint distribution. So basically trying to approximate the kth marginal at time k, the k plus 1th marginal at time k plus 1, and so on and so forth. Okay? So just a marginal of the full smoothing solution is what we want to characterize. Now, this is a problem that arises in many different settings, and today I want to really focus on a particular setting where we have state space models that have high dimensional states, challenging sort of nonlinear dynamics, for instance, chaotic dynamics, so governing that transition density. And in particular, I'm going to assume that the transition kernel is intractable, so I can't actually evaluate. I'm not going to let myself be able to evaluate pi of zk conditions on zk minus 1, but instead I'm going to say all I can do is simulate from it. So this is kind of a typical setting in numerical weather prediction. What I can do is obtain forecast samples. In other words, draws from, suppose I've observed up until today, I can run my model forward for the next 6 hours, and I can get a draw from this distribution of the state 6 hours from now, condition on what I've observed up until now. Okay? So the other thing that we want to get towards is limited model evaluation, so pretty small ensemble sizes. And I'm also going to make an assumption that's going to help us, which is that we have sparse and localized observations in space and time. So I'm going to observe, for instance, components of the state pointwise, or small sets of components of the state. Okay? And again, these are kind of constraints that reflect the typical setting for numerical weather prediction and other kinds of geophysical data assimilation problems. Okay? So it's filtering, but with these sorts of peculiarities. So practitioners would say, and this is sort of maybe an arguable point, that state-of-the-art results, and I mentioned state-of-the-art in what sense? State-of-the-art in the sense of tracking the truth in twin experiments, which is really perhaps has nothing to do with how well you capture the Bayesian solution, but state-of-the-art results in terms of tracking are typically attained with things like the ensemble common filter. And so this graphic is sort of my crude attempt to represent what the ensemble common filter is doing. Suppose I have samples of my state at some time z0. I'm going to use my dynamical model, here I call it a forward model, to essentially propagate these samples forward until some observation time, call it time k. And then I observe, say, have some observations here. You could think of this as contours of the likelihood. And I'm going to employ some kind of linear update to transform these samples from the forecast distribution to what I call the analysis distribution. So this I'll call the forecast, this I'll call the analysis. Equivalently, you could think about this as the prior and this is the posterior for the purposes of the single Bayesian update step that's happening at time k. Okay? So what the EnKF does, more or less, is move these samples, so move these draws from the prior via some linear transformation to some new configuration. And that new configuration is supposed to approximate the posterior in some sense. And it does so without introducing weights. So this is in contrast to particle filters. There's no importance weights, and there's no resampling. It's simply transforming particles, moving things around. Okay? Now, this is admittedly a crude approximation, and we'll talk about why this is crude and how to make it better. But the kind of philosophy underlying this is really, if you sort of step back, you think what it's really trying to do is think of taking the inference step and casting it as a transformation of measure. Okay? And so more broadly, we could think about, so what if we really want to cast the inference step perhaps more completely without these linear assumptions that the common filter makes, the ensemble common filter makes? What if we want to cast that step as a transformation of measure? How can we think about that? So one way to think about that is to suppose I have the prior distribution here, and this is my posterior. And one way to think about the transformation that it showed you is that it corresponds to a deterministic coupling of these two distributions. So here's my prior and here's my posterior, and I'm coupling them deterministically with this transport map T, such that if I apply T to samples X that are distributed according to the prior, what I end up with are samples that are distributed according to the posterior. So Z is my random variable distributed according to the posterior, X is distributed according to the prior. And essentially, in a crude way, what things like the EnKF are trying to do is approximate a transformation that moves you from here to here. So it's trying to trying to construct this kind of coupling. Now, in general, if I sort of gave you this post-prior and gave you this posterior, and assuming they're absolutely continuous, then some deterministic coupling will exist. But there's not just one, there's an infinity of them. And in general, unless, for instance, these are both Gaussian, the mapping T is going to be nonlinear. Okay? So what kind of transformations are we going to look at? What kind of transport maps are we going to look for? Various choices here, and we've actually seen some of them earlier this week. Cool things like the maximal coupling and things like that. Here, one that's probably familiar to everyone is this notion of optimal transport between two measures. So here, eta and pi are some measures, or I'll sort of overload them and think of them as densities. And the optimal transport says, okay, of all the different ways I could transform mass that's arranged according to eta to mass that's distributed according to pi, I'd like to do so in a way that minimizes some integrated transport costs. So this is, for instance, the starting position of the unit of mass. This is the ending position after applying the map T. I want to satisfy this condition on the marginals, but I want to do that in the cheapest possible way. Okay, so this is the optimal map, and this is very, it's well studied, it's very beautiful, it has many nice properties. But from the numerical perspective, it's a bit challenging in kind of general continuous cases to find optimal transport maps. The map that instead we're going to sort of use as a building block for the rest of this talk is the Noeth-Rosenblatt rearrangement, or the Rosenblatt map. And this is a map that is, let's say, lower triangular. Can be sort of permutations of this. Let's say lower triangular, where essentially it's a map from Rn to Rn. My densities are on Rn, but the first component is a function of only one variable. The second is a function of two, so on and so forth. And this also, again, sort of exists for absolutely continuous eta and pi. It's unique up to ordering, but it has some nice numerical features. For instance, the determinant of the Jacobian of this transformation, which we're going to need, is easy to evaluate because it's just a lower triangular matrix. The inverse map is also lower triangular. And maybe sort of a more foundational reason that this is going to be useful for us is that it actually exposes marginals as a function of a small number of variables. So in other words, if I want the marginal of the first variable, I essentially have a univariate transformation that gives me that marginal. If I want the marginal of the first two, I have only a bivariate transformation necessary to give me that marginal. Of course, which marginals you expose depends on ordering. And the other thing, this is going to enable conditional sampling, which again depends on ordering, but it's going to be, for instance, relatively straightforward to sample, say, the third component conditioned on values of the first two. So that's going to be useful for us later on. Okay. So it's going to be a building block for some more general, say, non-triangular transports. Okay. The other thing I'll just mention, this is kind of an aside, numerical approximations of this are nicer, they're easier to construct than approximations of a non-triangular map, because, for instance, to enforce monotonicity, which we would like to do, in general just requires that each of these component functions, say the kth component function, is monotone in the kth variable xk. And you can do that borrowing an idea from monotone regression, where essentially I have an exponential or perhaps some other positive function here, and then I use arbitrary parameterizations for these component functions a and b. So given whatever kind of approximation matrix I like to use, polynomials, radial basis functions, so on and so forth, I could insert them into these functions a and b, and this construction will guarantee that tk is monotone in xk. Okay, that's just a numerical aside. Okay, so back to this notion of EnKF. So you can think of the EnKF, the linear update that the EnKF constructs, as an approximate transform map. It certainly doesn't exactly couple the prior to the posterior. It transforms the prior to something else, but sort of tries to do what it can with the limited information that it has and linear transformations. So from this perspective, again, I think of prior as sort of, this P of zk. Here's this posterior. Inference in this context corresponds to finding a transformation T that pushes forward the prior to the posterior. Okay? Now, in the particular data assimilation context that is set up, we need to learn this transformation, unfortunately, from a pretty small ensemble, a small prior ensemble. So basically, we have samples from P of zk. And I'll have the ability to evaluate, for instance, the likelihood function. I'll talk about that in more detail, but this is sort of the constraints that we placed upon ourselves. And in the EnKF context, well, you say, well, I'm going to look for T that is a linear function, and even a linear function is too general for the EnKF given a small ensemble. So there's additional sorts of regularization that are imposed: localization, tapering, perhaps inflation, things like that. Okay? So a regularized approximate sort of construction of a linear function is what the EnKF does. Okay. Now, the question I'd like to ask that sort of motivates what I'm going to present next is, can we move beyond linear updates in a stable way? So, for instance, so what's wrong with linear updates? Where does the EnKF sort of fail? Well, as you probably all know, the EnKF is biased. It doesn't converge to the true Bayesian solution. For instance, if I add more particles, if I increase the ensemble size, I don't necessarily get closer to the true Bayesian solution. I don't even necessarily get better tracking performance necessarily. But then I would sort of say philosophically, under these computational constraints, perhaps we ought to trade some bias for variance. And the scheme that I'm going to propose will nonetheless try to navigate these trade-offs of bias and variance. More generally, you could say that the linear updates limit tracking ability and certainly uncertainty quantification. And by that I mean your ability to actually approximate the Bayesian solution, limit the uncertainty quantification ability of the filter. And that's something Cody showed in a paper several years ago. Okay, so some questions that I'd like to try to address or begin to address. First is, okay, as I said, the EnKF is not guaranteed to perform better as you increase the ensemble size. So can we mitigate that? Can we get closer to the Bayesian solution in some sense while preserving the robustness of EnKF type approaches? And then along the same lines, what is the best one can do in the sense of closeness to the Bayesian solution with a given ensemble size? Okay, so we're sort of tackling this problem from the perspective saying, here are the computational constraints. Given these constraints, what can we actually do? And that philosophy, maybe that's a very practical philosophy, but I think it's an interesting question to ask. So, okay. To make this work, we're going to have to, much as the EnKF does, employ regularization. And in that sense means we need to think about structure in the prior and the posterior, structure in the forecast distribution, structure in the analysis distribution, and how can we actually use that structure? So what are the kinds of structure that we might see? Can I actually touch this here? No. So for instance, I mentioned we might have localized likelihoods. So the observations might be only depend on one component of the state at a time or a few neighboring components of the state. There might be some decay of correlation or dependence, and this is thinking of across the state. So within this distribution here, this is a distribution over, say, n variables. There might be some faraway variables might not be so correlated with each other. The other property that I'm going to sort of focus on is that this distribution might have some Markov structure, some approximate Markov structure that we could take advantage of. So some conditional dependence relationships inside of this distribution that we're going to use. And then other things, this is not meant to be exhaustive. I would say there's other things like low rank structure and so forth, so on and so forth, which I won't really talk about too much today. Okay, so we're going to try to use these structures to construct filtering algorithms. So we want to use this kind of structure and understand the structure of the prior to posterior update. Okay. So here's kind of the core idea of how the algorithm is going to work. We're going to begin with a forecast ensemble, and we'd like to transform that into approximate, necessarily approximate, because given the computational constraints, approximate samples from the filtering distribution with local in a sense that I'll describe more precisely later on, low-dimensional and nonlinear transformations. And the way that we're going to do this is we're going to essentially take the forecast distribution and the posterior and project them onto some manifold of sparse but non-Gaussian Markov random fields. And this is going to give us some necessary structure that we can use to design the transformations. And the choice of sparsity is a regularizing assumption that we're going to impose. And we're going to introduce, in this context, we're going to have the ability to introduce nonlinear features. Even given limited ensemble sizes, the idea is we'll be able to learn nonlinear features of these transformations, but in a stable way. And you could say that the algorithm I'm going to propose maybe reverts to the EnKF as the transformations become linear and as other sorts of regularizing assumptions that we impose become relaxed. Okay. So a couple ingredients before I kind of describe the whole algorithm, maybe just 3 different ingredients. So the first ingredient is just the notion of a Markov random field, in particular in the non-Gaussian case. So the idea here is suppose I have some distribution, some joint distribution of n variables. Think of this as my n-dimensional state of my dynamical system, at a given time. And with this distribution, I can associate a graph where see every vertex here corresponds to one of these scalar random variables. And the lack of an edge implies conditional independence. So here it's just kind of a pairwise conditional independence property that you can read off of this graph. And the idea is that given some Markov structure, and it's a separate question perhaps how you find the Markov structure. Here we're going to impose it. I'll talk a bit about that later on. But given Markov structure, I can actually associate that with a sparse coupling of this distribution to, for instance, some other distribution that I'm going to describe. So in what sense? So this is a result that we developed pretty recently. The idea is as follows. So suppose I have some distribution, call it pi 1. That's a product form distribution. So its graph has no edges. It's a product of independent, it's a product of its marginals. And some other distribution, pi 2, that has this Markov structure. Then I could imagine, okay, a coupling T that pushes forward pi 1 to pi 2. And then the inverse of T, I'll call it S, that takes pi 2, transforms it back to pi 1. S enjoys some sparsity properties that I can read off of this graph before I actually compute the transformation. So in particular, so the result is essentially a result about the sparsity of lower triangular maps. And the sparsity is coming from numerical linear algebra. It's really the same sparsity as the Cholesky factor of an incidence matrix of this graph with some sort of permutation and rescaling. Okay? And so for instance, for this graph here, we can basically read off that rather than S being a full lower triangular function, it's a function only, so its component functions can only depend, S4 would only depend on Z3 and Z4, S5 would only depend on these variables, so on and so forth. So given the Markov structure, I can correspondingly predict the sparsity of S. And in fact, these are just kind of lower bounds on the sparsity. S might be a little bit more sparse in some sort of particular cases. But you can read off bounds on the sparsity of S before you actually compute S. Now, how do you do it? Well, this is just kind of an aside of how do you compute the sparsity pattern. So suppose I begin with some 5-dimensional distribution, and I've labeled the nodes as follows. So it's Markov with respect to this graph. Essentially, what I do is something kind of like a variable elimination. I remove the ith node. I'm going to start with the last node and turn its neighborhood into a clique. So I remove 5, I get 4, 3. I remove 4, I get this. I remove 3, and then I have to connect 1 and 2. And the sparsity of the inverse transport of this S essentially depends on what are the variables in the neighborhood of your particular node in the ith graph in this sequence. Okay? And this is basically, same kinds of thing that happens in a sparse Cholesky factorization. Ordering, of course, matters very much, and I'll talk a bit about ordering. We need certain orderings for our conditioning schemes to work. Finding an optimal ordering, one that minimizes the fill-in, one that makes this as sparse as possible, is in general an NP-hard problem, but this is something people have thought about a lot, and there's some good heuristics for this kind of thing. Okay, so the key takeaway from these 2 slides is the relationship between the Markov structure and the sparsity of this map S. Okay. And I want to emphasize this is applicable in the fully nonlinear non-Gaussian case. If we reverted to the Gaussian case, then the sparsity, then basically the sparsity of this graph corresponds to the sparsity of the precision matrix. And what we're doing, you can think of this map S in the Gaussian case, if these are both Gaussian, as the Cholesky factor of the precision matrix, okay? Which is going to transform your correlated normal back to an uncorrelated normal. Okay? But this is general for the non-Gaussian case. Okay. The second ingredient, before I kind of construct the algorithm, is this notion of conditional simulation from triangular maps. So this is the other reason triangularity is kind of nice. So let's begin again with some map S that pushes forward my complicated distribution pi to a simple distribution eta. Eta is a product of marginals. And suppose I have this triangular map. But now let me consider a different triangular map that essentially comes from chopping off the head of this map S. So essentially this map chops off the first k components of S and leaves only k plus 1 through n. And I'm going to fix as a parameter of this map the values of xi, 1 through k. And essentially think of this as a triangular map in variables zk plus 1 through zn. So if I sort of outline this area here, these are maybe think of them as the active arguments of the map, and these are just some parameters that are along for the ride. Now this map actually pushes forward the conditional of variables k plus 1 through n, the variables k plus 1 through n, conditioned on variables 1 through k, to the marginal of the reference distribution. So if this eta is a standard Gaussian, which is typically going to be, then essentially I'm saying I have a map that's going to transform my conditional of interest to a standard Gaussian, and I could invert that map to draw samples from my conditional of interest. And there's like a draw samples from this Gaussian and evaluate S inverse on these samples, and I would have samples from this conditional. And a triangular map is relatively easy to invert because inverting the triangular map essentially amounts to a series of one-dimensional root finding kinds of problems. So the idea here is that given a triangular map with this particular structure, I can condition variables further down in the ordering on variables that are on the top. Okay. Now the third ingredient is, well, how to actually construct these maps. And there's going to be two sorts of calculations that are involved in our approach. One is maps from samples. And this is actually sort of maybe the workhorse algorithm of the approach. And the idea is as follows. So suppose I have samples from my distribution pi, and I'd like to find a map S that pushes forward pi to eta, or equivalently, I can find a map S that pulls back eta to give me pi. And I'm going to find this map S by minimizing this KL divergence written in this particular order. And it's written in this particular order because this KL divergence involves an expectation with respect to pi. And I'm going to minimize over a set of monotone triangular maps, and I'm going to be able to impose, for instance, sparsity structure in this set, curly S triangle. I'm going to say I'm going to only look for maps that have this particular functional dependence on all its components. And the nice thing is that for Gaussian eta, this problem is actually quite nice. This is an easy optimization problem. It's convex. It's separable in the sense that I can find every single component of the map independently or in parallel. And if I sort of write it out more carefully, this is essentially what it comes down to looking at. So basically, you have the map S sitting inside here. We have the square, and then this essentially comes from the Jacobian determinant term, and I have this monotonicity constraint. Okay. So this is given a set of samples, I can construct a map, and I can enforce sparsity in that map by choosing the approximation space curly S triangle appropriately. Of course, I need to also decide if S is in general nonlinear, I need some finite dimensional approximation space. So what functions are going to be in curly S triangle is something I'll talk about as we go ahead. Okay. The other kind of calculation that will happen is rather than maps from samples, we may also need to construct maps from unnormalized densities. So given the ability to evaluate a density pi up to a normalizing constant, the sort of dual of the problem I just talked about is to say, now let me find a map T that pushes forward my standard Gaussian reference to pi. Equivalently, I can write it this way. So let me find a map T that pulls back, whose pullback applied, that pulls back pi, whose pullback through, no, the pullback of pi through the map is eta. But again, now this is, again, minimizing the KL divergence. I've reversed the order. Now this is perhaps a more challenging problem in general, because now, okay, the expectation is fine, expectation with respect to the reference measure, but this is not in general a convex problem. It is only convex if pi is log concave, and in general does not separate across the dimensions the way that the previous problem did. Nonetheless, this is essentially, think about this as basically like a variational Bayesian problem. It's the same functional that people minimize in variational Bayesian approaches in general. And what I'm essentially trying to do is say I have some distribution pi. I'd like to approximate it by some member of the family of distributions that I can achieve by pushing forward eta through some set of maps, curly T triangle. And so I want to minimize that. And just to kind of give you an example of how that problem works, so if I kind of rewrite the objective, it looks like this. Essentially, it involves So now I'm going to have expectation over the reference. I'm trying to find a map that minimizes this. So this actually says, okay, I want to find the map that puts the samples in regions of large log pi to make this small. And then this, which comes from the Jacobian determinant, essentially says I don't want the samples to all collapse to one point. You can think of it as a sort of a repulsion. I don't want the map to become too flat. But what I can do, solve this problem. So I can, for instance, parameterize the map in some finite basis, and I'll talk more about that later on, and solve the problem as follows. And this is, and I can just use gradient-based optimization. So here, this is sort of a cartoon where what I'm showing you is actually iterations of the optimization that we use to find this map. And at each iteration, I'm showing you the push forward of reference samples eta through the map. I begin with an identity map, so the samples are sitting right here on the standard Gaussian reference. And the target is out here in the tails of the reference. And we solve the problem. This is one iteration of using BFGS, the quasi-Newton method, 2, 3 iterations. And the samples are essentially transformed to look like the target distribution. Okay? So this problem is more costly, but using gradient-based optimization, you can actually almost tackle these problems where the reference and target are mutually singular, almost. Okay? So I think that's the ingredients, and we're going to now put all these things together. But I just should comment that the workhorse of the algorithm I'm going to describe is actually the maps from samples. We will solve the maps from densities problem, but that maps from densities problem is going to be, in the algorithm I described, very low dimensional. Its dimension corresponds to the locality of the observations. So if my observation depends on one component of the state, then we're going to solve this problem in one dimension. And if the observation depends on multiple components of the state, then we're going to solve that problem in higher dimensions. Okay. So back to the filtering algorithm. So what is kind of our goal, the name of the game? We would like to find a transformation from the prior to the posterior. But the prior and the posterior in general have some arbitrary Markov structure. And in general, so if I want to couple this distribution with that using a Rosenblatt rearrangement, there is no sparse prior to posterior update in general. But what you can do is introduce a bridging distribution that's a product of marginals. And I could say, let me find a transformation from the prior to this bridge. Let me call that S1. And let me find a transformation from the posterior to this bridge. Let me call that S2. And now the composite, each of these might be sparse because these correspond to, if these graphs are sparse, then I know there are sparse maps that will sort of sit on both of these edges of the triangle. So I can compose these sparse maps together, and their composition might not be sparse, but I can find the elements, the two maps separately. And that's what we're going to try to do. So to kind of describe how this works, just for simplicity, I'm going to consider assimilating one observation at a time. And you can generalize this, but I think it's probably easiest to understand if we do one observation at a time. So the idea is as follows. I have my prior, I have my posterior. I'm going to map each of these to some bridge distribution. You can think of this just as standard Gaussian in however many dimensions you need. And the idea is that we can show there exists a nonlinear update T that transforms the prior to the posterior when the posterior basically involves conditioning on one local observation that has this particular form. So S is going to be a triangular map that pushes forward the prior, or the forecast distribution, to the standard Gaussian. Tau is something that I'm going to describe, and then script S is something that I'm also going to describe, but mostly involves S. Okay. So the idea is that I'm going to construct a map T that's going to take me from here to here, but I'm going to build its components by appealing to this auxiliary bridge distribution. Now I'll describe how that actually works. So kind of key steps of the algorithm. So we're in a setting where, like in the Ensemble common filter, you have propagated samples of the previous filtering distribution forward in time to the new assimilation time. These are samples from the forecast distribution. And we're going to approximate that forecast distribution. We're going to assimilate each observation with a map, and then we're going to propagate that observation across the state. And that's essentially these three steps, 1, 2a, and 2b, correspond to this map here. This is going to approximate the prior. This map here is going to condition on one local observation, and this map here is going to spread that information across the state, if you will, sort of intuitively. A distillation of this problem, which I think is just kind of interesting from the, because they come from inverse problems, from Bayesian inverse problems. In this problem, essentially, we have samples from the prior, perhaps a limited number of samples from the prior, and I have the ability to evaluate the likelihood directly. Okay? that's the essence of the whole update step. Given those ingredients, this is what we're trying to tackle. I should mention there's related ideas in what's called the rank histogram filter from Jeff Anderson and Chris Snyder and company, and that filter sort of couldn't scale beyond a handful of dimensions. And what we're going to describe here essentially tries to address some of the issues that were in the rank histogram filter. Okay, so let me describe that first step. So the first step is actually what we just saw before. So I have n forecast samples. These are samples from the prior. I'm going to find a map that pushes forward that forecast distribution to my bridging distribution eta. And I need to pick a parameterization for each component of this map S. I'll give you some examples for that. But I'm going to basically solve the optimization problem that I described before. This is the maps from samples problem. I'm going to find all these elements in parallel. Okay. Now, I want to do this with a limited number of samples. So to make this work, I need to impose some sparsity on these map components S. And the imposition of such sparsity is essentially a regularizing assumption. I'm going to impose it. Later we can talk about learning it, but for now I'm just going to actually impose that as a form of regularization. And you can think about, for instance, the sparsity I might do if you come from ensemble common filtering. Something that people often do is localization. And you could imagine doing localization in the Markov structure of the forecast distribution, where I say each node, each random variable, has probabilistic interactions with some neighborhood. So basically, I'm going to impose some level, two-way, three-way, four-way, five-way interactions between nodes and their neighbors. And that's going to give me sparsity of this map S. Okay? That's the first step. Now, the second step is, okay, now, suppose I want to assimilate an observation of this one node. So suppose this is the Markov structure. Suppose this is the Markov structure of my state. And I observe the node that's in red. And now I want to condition on that scalar observation. So let Z be all of the state, all the elements of the state. And I can factor this as follows. I can say, okay, Z1, because of this conditional independent structure here, I can say, well, this just factors as Z1 condition on Y, and then Z not 1, everything else condition on Z1. And what I'd like to do in the local assimilation step is essentially capture or characterize this posterior marginal, Z1 condition on Y. So I want to transform the marginal prior on Z1 to the marginal posterior. And what do I already have? I already found a map S that takes all the marginals of the state and transforms them into standard Gaussian. And let's say that I put the observed node at the very head of that map. And I actually need to do that because I'm going to need to condition on that later on. But suppose I put that first node, node 1, at the very head of the map. Then I've exposed its marginal with a one-dimensional transformation of a Gaussian, because the Rosenblatt map exposes marginals in that ordered way. So that first map S essentially pushes forward the prior on Z1 to the standard Gaussian. Equivalently, I could say, let me just pull it back, I've constructed an approximation of the prior that is the pullback of the standard Gaussian through the first component of the map. I can write that prior here in red. The likelihood I can evaluate in closed form, and now this is my target density. Okay. And now I'm going to look for a map tau that pushes forward the standard Gaussian to this target density. Now this is the maps from densities problem. This is one where now I actually parameterize the map and solve this problem by minimizing KL divergence in that second sense. But this is a one-dimensional maps from density problem. It's actually quite easy. And there's other ways I can construct this map. I don't necessarily have to look for parameterized maps in some way. I could look for just the increasing rearrangement. I could approximate the CDFs in some way. There's a zoo of things that one could do here. But this is a one-dimensional maps from densities problem. Now, having done that, then the composition of S1 with tau does what I want for the first marginal. It transforms samples of Z1, prior samples of Z1, to posterior samples of Z1. Because S1 takes you to a Gaussian, then tau takes you from a Gaussian to the posterior. So having done that, now essentially I want to say I've conditioned this node on this observation, but now I need to condition all the other nodes on this observation. And that involves, by the conditional independence assumption, essentially simulating from this conditional of Z not 1 conditioned on Z1. Okay? And that uses the conditional simulation strategy that I've just described. If 1 was the head of the map, then essentially I need to sample from Z2 through Zn conditioned on Z1, and essentially I'm going to use this map to do the conditional sampling. Okay? So this is an element of that map that described the forecast distribution that I found in the very first step. But now I'm just going to use the rest of it. And of course, this map is in practice going to be sparser. So if I put all this together, then this is the combined map. So I have S, I have tau, which transforms my prior marginal to my posterior marginal in the observed node. This is just the identity here. And then here is the identity, and this is the inverse of the lower part of the triangular map S. Okay? So this combined map transforms the forecast ensemble to the analysis ensemble. Now this is all this work, you say this is just for one observation, but I can now iterate this construction to do each additional observation, or I can sort of generalize this to do multiple or batch observations. Okay. So, okay, the kind of final thing I want to show before getting into some numerical example is, where does regularization enter into all this? Like, what are the various forms of sparsity in the map? So the key sort of ingredient of all this is this map S that transforms the forecast ensemble to a standard Gaussian. And this is where I have a limited ensemble. I can't learn this map, I can't learn a map of arbitrary complexity. But there's various knobs here where one can deduce essentially regularization. So the first one that you could do is, for instance, say, well, because of the conditional independent structure of the forecast, then this head of the map is going to be sparse. The other thing I could do is set the remaining map after some, maybe say the correlation length of the forecast distribution. I could actually set this map from k+1 on just to be the identity. I mean, the real lower triangular map that represents the forecast doesn't necessarily do that. But if I know that I'm going to use this map only to capture the impact of this local observation, and if the correlation length of the prior is limited, then this map will in fact revert to the identity. So I can impose that reversion as a form of regularization. And then also, there's going to be regularization through the choice of basis functions that I actually use to construct the head of this map. Okay? And if I think about what this map actually does, if that's sort of the map S composed of this and composed with S inverse, its action, especially if I set this all to the identity, is going to be local. So if I assimilate an observation here, it's going to propagate that information across the state up until the point where this reaches where this is imposed to revert to the identity. Okay? So these are many different forms of sparsity that one can impose. So let me give you a numerical example. So this is Lorentz 96 system. This is kind of a common chaotic dynamical system that people use as kind of a prototype for numerical weather prediction problems. The state is 40-dimensional, and we are sort of running this in a chaotic regime with this forcing term here. We have a relatively moderate observational noise on observations. We're observing every other element of the state, and the time between observations is actually quite large. So this is actually a challenging configuration of the problem that people have looked at in the literature. And what I'm going to do here is sort of like the algorithm I just described. I call this a localized nonlinear filter with a certain number of particles. Here is tracking error. So this is essentially the root mean square error of the filter. So I essentially run I run a trajectory. I get the truth. I generate data. Given that data, I construct an estimate of the state. I'm taking the mean of my particles to be the estimate of the actual state, and then comparing that to the truth. And this is, sort of want to lay out, does not approximate how well this thing captures the full Bayesian solution, but this is the diagnostic that is sort of available to us easily, and this is the diagnostic that people use. So if you use the EnKF, this is actually EnKF, borrowed from this paper of Bengtson. Basically, the EnKF gives you an RMSE that's about here. With the same number of particles, we can reduce the RMSE substantially, which is, and say 25% is actually nothing to sneeze at in this context. It's hard to reduce this often by more than a couple percent here and there. With a smaller number of particles, we have the same kind of reduction. And here what I'm doing is not comparing to kind of a literature EnKF, but saying, what is the impact of actually introducing nonlinear features? So if I run the filter with essentially linear maps, and if I run the filter with nonlinear maps that I'm going to describe in a second, then the RMSE is able to be reduced substantially. So it's sort of saying that these nonlinear elements of the transformation have a practical impact on the ability of the filter to track. Now, how did we do that? We assimilated the observations one at a time. The prior, the Markov structure that we imposed was essentially 5-way interaction. So the state of the Lorentz 96 system you could think of as a ring. And what we essentially said is that each node interacts with its nearest neighbors and then its next nearest neighbors. Okay, so that's the Markov structure that we impose, given the sample set. So as a result, we're only learning maps that are essentially each component of the map is essentially 5-dimensional, given the ensemble size. Now, you have to choose, okay, how am I going to represent this nonlinear map? What particular representation am I going to use? What we used here, and I'll argue for this is actually kind of generally useful, is a separable nonlinear parameterization. So the size are nonlinear functions, but here in this map that we learned, there were no cross terms. So elements of the map did not interact with each other multiplicatively, and these size are essentially a combination of a linear term and then some radial basis functions. This is one choice. This is one sort of practical choice, but many more general things are possible. Okay. And just to kind of give you a picture of the tracking performance, so this is the truth. This is the state, sort of in color contours. This is time on the vertical axis. This is the dimension. You can see the dynamics are relatively interesting. And this is the truth, and this is the actual mean of the filtering distribution. So having these simple nonlinearities, essentially only through these choice of radial basis functions constructing the map, has some interesting practical impact. OK, so a lot of things to discuss. One natural question you might ask is, OK, how does one choose the representation of the map? Now, this is sort of a wide, open, flexible thing. I'd argue that it's a feature more than a bug, but it's a feature that one has to navigate. What we used were separable parameterizations of maps, of the map S in this example. And you could think of this as a kind of a natural increment beyond linear maps. So if S were linear, then there's essentially obviously no cross terms involving the different x's. And we retained that structure, but allowed the function as a function of each variable individually to become nonlinear. And we sort of retained a linear term here, and then added some localized nonlinear functions. This particular, so the separable parameterization actually has a lot of practical computational benefits. So solving the optimization problem of maps from samples essentially reverts to a regression problem. And inverting the map and doing conditional sampling is very easy in the separable format. So there's computational reasons to choose that, but that's by no means exhaustive. There's many further possibilities that we're honestly still exploring. On the overall scheme, in philosophy, this is like an ensemble common filter. So there's no weights, no importance sampling. We're moving the ensemble members, and we are definitely accepting some bias. The core idea is to learn the non-Gaussian features of the forecast distribution by solving this convex optimization problem to find the map S. But you could think of, as the map S, as the approximation space for the map S is enriched, and as the ensemble size correspondingly increases, and these things have to increase simultaneously, the filter becomes, is consistent. So in that sense, the construction that I derived, where we said, OK, we have the map S, we have the transformation tau that approximates conditioning on one variable, and then we have the inverse of the map S, that you can think of that as showing the existence of a map that will exactly transform the prior to the posterior, given that Markov structure. Exactly transform the prior to the posterior, given that Markov structure. Now, we step back from that and we start making numerical approximations. And the numerical approximations are necessarily dictated by the small ensemble size. But you could think about that flexibility as an opportunity to fill in some of the territory between a fixed parametric approach, like the EnKF, and a completely non-parametric approach, like the particle filter. Okay? Now, within that territory is vast. And how to navigate that sort of optimally, I do not yet know. But this is sort of offering a construction that can do that. The choice of the map basis and of the Markov structure are essentially the things that give you regularization. And I would argue that if the ensemble size is small and the state dimension is high, then you have no choice but to impose this kind of structure. OK, so a couple extensions. You can also do things, I didn't talk about this, but you can sort of do parallel strategies for conditional sampling and simulating multiple observations, essentially by decomposing the graph. So given the Markov structure that you impose on the prior, you can do that. But the natural sort of next questions are, now given an ensemble size M, how do I balance things like nonlinearity in the map with sparsity? Should I be more sparse and more nonlinear? Should I be less nonlinear and more sparse? Or should I be more nonlinear and less? Should I be more nonlinear and more sparse, less nonlinear and less sparse? These are choices that one has to think about. And the other natural question is, can you use, for instance, regularization penalties to learn sparse maps from samples? And then I'll give you a preview of that in the next couple slides. But again, I want to sort of reiterate that this filter is consistent as the approximation space of the maps is enriched and as the ensemble size goes to infinity. But understanding what the bias is given a particular parameterization and what the variance is given a particular ensemble size might help navigate these trade-offs. And we're just at the outset of this, and certainly a lot of error analysis is needed. Okay, just a little preview. Learning sparse maps from samples. So one thing you might say is, right now we have imposed Markov structure, for instance, those 5-way interactions, as a form of regularization, using the same philosophy that people impose do things like localization in an EnKF. If you wanted to get away from that and you said, my hypothesis is simply that there is sparsity. There is sparsity in this graph, and correspondingly there is sparsity in the coefficients of this map S, but I don't know its particular configuration. how can I recover maps, and how can I do that in a particular in the setting of very few samples. So a natural thing to do is to think about all the literature on sparse recovery and solve an L1 penalized problem to estimate the map coefficients. And this is sort of a preview of some current work. And this actually is nice because it seems that it gives us the ability to learn maps from very few samples, where the number of samples is much smaller than the ambient dimension D. And so here, essentially, I'm looking at error in the coefficients, error in the KL divergence for the approximation of a forecast distribution. And if I impose no regularization, then essentially, this is a 40-dimensional problem, or no, this is the number of coefficients. So I need at least as many samples as coefficients before I can learn anything. That's the black lines. If I impose an L1 penalty, then I can learn the map to some degree of accuracy with a much smaller number of samples, and compared to the oracles, if I actually know the sparsity of what generated the data, then I can do that. And there's a result, essentially, this is a similar kind of result that you see in a lot of other sparse recovery literature, that the number of samples can scale as order S log D to be able to recover the map in high probability, where D is the ambient dimension and S is the sparsity. Now, so far we've been able to show this only for maps that are linear on the diagonal and nonlinear on the off diagonal. And that corresponds to basically a particular choice of certain conditionals are Gaussian. So this is not yet established for general non-Gaussian distributions, but that's sort of work in progress. The other thing you need to do is sort of control the tails of the distribution. They need to be sub-Gaussian for any of these results to hold. So yeah, and this is just a different example. Okay, so I think I was going to talk about smoothing, but there's probably zero time for that. Okay, so I'll say one thing on smoothing, and then I won't talk about So I want to put this in some sort of broader context. So in what I've talked about today, we've been looking at structure within the state. So essentially, I've been talking about the Markov structure in the forecast distribution. This is basically saying something about conditional independence relationships among elements of the state. In some related work, we've looked sort of at a more macro level across the states to come up with transport approaches to smoothing and joint state and parameter estimation. Now, there are links between that and what I talked about today. I want to say in that work, sort of came in with a different assumption. We assume that this density is tractable in the sense that I can evaluate it, I can take its gradients, I can sort of use the full variational Bayesian machinery to be able to tackle this problem. And that's sort of nicer in the sense now you can say something about how close you are to the Bayesian solution. You can make the approximation arbitrarily good. You have a lot more sort of fidelity at your disposal. You're not constrained by this, I only have samples from the forecast and limited number of samples from the forecast of that to do things. But nonetheless, you can use, this can be relaxed, and you could use, envision sampling-based approaches to the same kind of smoothing approach that's described here. And similarly, you can impose that within state sparsity within the variational approach that we described here. So there's a link between the two. I don't have time to talk about the details of either one. Some slides later on. So I think I will just leave it at that and put up some references. So thank you very much for your attention.
It's quite a bit of interest in this sign variational approximation, where you put a little space and then you get the vector field that transports your particles, and it seems related somehow, right?
Yeah.
Or some sort of structure of the vector field.
Yeah, yeah. Yeah, no, so the standard variational approach is very interesting. I would say that, in their kind of current incarnation, the way that people have played with them, and we've been playing with them too, they work in the setting where you can evaluate the target density. And I want to, say, transform some initial set of samples or whatever to this target density. And you could think of those standard variational approaches as basically being a non-parametric approach to variational inference. So when I construct a Rosenblatt map, and I parameterize it using some basis functions, it's very much a parametric approach. And you can worry about, maybe it's semi-parametric because you can sort of enrich the parameterization. But the Stein variational approach is non-parametric in the sense that the complexity of that transformation is dictated by the kernel that you pick and then the number of points that you have. And as you put more points, then in principle that thing can become more complicated. So it very much, I think it actually has applicability here in the setting where you can evaluate the target, where you can evaluate the transition density. It's less clear to me how to use it. In other words, I think it can solve the maps from densities problem. not so clear to me that how well it will solve the maps from samples problem, but maybe. So I think it's very interesting. I think it has a lot of connection.
The structure map, I guess, like and the hash matrix, right? But usually hash matrix, when you're dealing with like the non-Gaussian distribution, it's going to be different at certain point of the space, and then it's in principle like your structure map could change from the space, like at one point in space.
Right.
I think here you're like the same, like everywhere in space, or
Yeah.
is there like way you can adapt with
To do that, yeah. So okay, so here I just want to be clear, like in what I presented here, we're not trying to learn the structure. We're imposing the Markov structure and then working within that Markov structure. In separate work, like we have tried to learn the structure, and there is this, yeah, just to so it's clear what Shin is talking about. There's basically, if you have some joint distribution of n variables, you can say that xi is conditionally independent of xj, conditioned on everything else. If and only if the Hessian, say the ijth element of the Hessian of the log density is 0. But this is a function of x. And so it has to be 0 everywhere for this to be true. Now, you might ask, okay, what is, if it's near 0, mostly like, is this like a weak link? So I think that really leads to this notion of approximate sparsity and approximate conditional independence. The sort of thing you'd like to do is to relate something like this to conditional mutual information, which you could say is sort of, so it's hard to interpret what's the magnitude of this, what is the magnitude of the expectation of this entry, how does that relate to something? But I think we can relate this to conditional mutual information, but that's just kind of a hunch. And then you could maybe say something about if I neglect weak links, what's the error that comes and things like that.